Good morning, ladies and gentlemen. Welcome to the webinar. And if you have observed, those who are participating are 90% of regular participants who decided to enlighten their knowledge, and they are quite regular. And also very surprised to see some of the college electrical department is broadcasting into the classes and to the student from one link. In Bangalore, I know there are two colleges is broadcasting this webinar for their electrical students. And similarly, I'm sure we have almost 560 participants today, including these colleges. We have over 1,000 plus people. Majority of the students are regularly participating, and we are getting enormous testimonial and comments that these sessions which we are doing in every Saturday is, for most of them, it's a surprise. Sometimes it is a new learning about electrical installation. So I once again welcome today, 5th of August. This is our 14th NFE webinar which we are doing. And Mr. Shiv Kumar, who is going to be our speaker today, is conducting for the second time. We have our moderator, Mr. S. Gopakumar, who will also join me in this program. This program is initiative of National Federation of Engineers for Electrical Safety, in short, NFE. Those who don't know NFE, this is just a 4 months old baby. The society was born and it's broken all the records. When I say all the records, one of the fastest growing society in India with over 550 plus members. And in record, we have done almost 14 physical seminar on National Electrical Code of India in association with Bureau of Indian Standard. Yesterday, we had a very highly successful program in Pune. And BIS and NFE presented, we had a very detailed presentation on NEC 23 and also panel discussion. Our mission is very clear: to make every electrical installation free of accidents such as electrocution and fire due to short circuit, and increasingly the reliability of the electrical installation, thus contributing to the savings of lives and property, and supporting sustainable development of the nation. With good intention of the vision and mission, we have become one of the fastest growing society. We would like to see all the electrical engineers in the country. I'm sure it would be over 2 to 3 lakh in electrical engineers in the country. They all coming together. Only when you come together, the change begins. So I'm sure you will join NFE and become a member. In case you are yet to become a member, and those students who are listening, we have a very subsidized membership fee for students. So I would urge all the participants to join NFE and strengthen the nation development. And our next coming up seminars, we will be in Bhubaneswar on 18th August. And we will be in Mumbai for the opening of the chapter on September 8th, September 29th in Coimbatore, and last leg of this NEC program will be concluded in Gurgaon on October 13th. And our next Saturday, 19th August, which is Saturday, we'll be talking about overcurrent protective devices. Very interesting subject. Will be delivered to you by youngest consultant in India, youngest engineer, Krish Theobald. And he's been participating in as a speaker in almost all our NEC program. So he will be talking about overcurrent protected devices. And ladies and gentlemen, today's program We're going to talk about earthing, solidly earth system and resistant earth system. And welcome once again. And through this session, we will explore the differences between solidly earth and resistant earth system. Understand their unique characteristics and discuss their advantage and limitations. Our team of experts are meticulously researched and compiled valuable insight on this topic, and we are excited to share our finding with you. We will cover important aspects such as the design consideration, implementation challenges, and the impact of earthing systems on overall power system stability. Thank you once again for being part of this learning experience. Let's embark this enlightening journey together as we uncover the intricacies of solidly earth and resistance system. Requesting all participants to put your questions in Q&A box below your chat box, you can see there, and engage with our team. And I would request all the participants to touch only on the subject that we are talking. Our speaker is expert on the subject, so let's not deviate your question with any other electrical related. So I would request, please put a question related to today's topic. Let's get started. I would like to introduce our speaker, our moderator first, Mr. Gopakumar, who is there and is a well-known face in almost all our lecturer, and is very actively with BIS and International Electrical Code. So he will be there. He is there today, and he will just begin with one opening remarks before welcoming Shiv Kumar. And Shiv Kumar, a very active member and very experienced, very learned, with 40 years of experience in wide variety of low voltage, medium voltage, high voltage, extra high voltage, electrical equipment in various electrification projects and process industry. He has been conducting training programs on various electrical engineering topics. He worked with L&T as a trainer, and he continued to share his experiences and knowledge to the young engineers of this country. So I would now welcome our moderator. Sir, Gopakumar sir, are you there? Will you be able to say a few words before Mr. Shiv Kumar joins?
Yes, good morning to everybody. So today we are going to discuss a very important subject of earthing, resistance earth system, solidly earth system and resistance earth system. And we have the best speaker in India on this particular subject, whom I have seen, where I have seen. So welcome Shiv Kumar sir, you can start your session sir. So I will coordinate for the question and answers. Thank you very much.
Thank you sir. Thank you.
I will upload my PPT.
Yes, sir.
Yeah. One minute. On the reading book. Reading. No. Hello. Hello. Can you see the window?
Yes.
Yes. Yes, sir.
Yes.
Yeah. Good morning to all the participants. Last July 1st Saturday, I have conducted a webinar on unearthed system. This is a continuation of that. I am honored to share my knowledge and experience with the members and members of the SFP and other participants. Can you hear?
Yeah, one moment. I think the last line of the presentation is not visible. Probably.
No, that is only.
Huh?
Last line.
Last
Now,
I can see, sir, full.
Okay.
Now it is there.
Yeah,
we
yeah,
are
yeah.
able to see.
Yeah, I can see full, sir, full screen.
Okay. That is only my name and phone number, sir.
Okay.
Okay. Good morning once again, everyone. We will continue. Please, last time also I was able to answer most of the questions participants asked. I request the participants to feel free to ask questions. I will try to answer them to the extent possible. So I will move on. Last webinar, we have discussed about unearthed system, advantages and disadvantages. Today we will move on to earthed systems. So whatever the disadvantages of the unearthed system becomes automatically the advantages of the earthed system. So we will proceed with the methods of system earthing. Please remember, we are discussing only system earthing here. System earthing in the sense earthing of the current carrying conductor, that is mostly neutral of the transformer, neutral of the generator. So here there are 4 methods of system earthing practiced: solid earthing, resistance earthing, reactance earthing. It is normally called inductance earthing or reactance earthing, and Peterson coil earthing. We will discuss one by one. Maybe this session we will have solid and resistance. Maybe in an upcoming session we will discuss the other 2. Now, the moment we announced this topic, immediately there were a plethora of questions from many engineers, experts in the field. Should we not call, why are you calling solid earthing and resistance earthing? Should you not call this effective earthing and non-effective earthing? You should not call solid earthing and resistance earthing or impedance earthing. It should be effective earthing and non-effective earthing. That is what many people raised the question in the WhatsApp group of NFE as well as in private chats with me. I will try to answer that. This question has been asked before also when I was conducting earthing training programs on behalf of L&T. These questions have been asked many times before also. I will try to answer this. So if you look into the Bible of earthing in India, that is IS 3043, if you make a effective earthing search, at least in only one place, the Indian Standard Code of Practice for Earthing mentions effectively grounded LV system in a certain class 5.6.2. It mentions in an effectively grounded system what will happen. That's all. But it does not explain what is an effectively earthed system or what is a non-effectively earthed system. There is one passing by mention of the term effectively grounded system in IS 3043. And other than this one area, one class 5.6.3, there is no mention of the term effective earthing or effective grounding anywhere else in IS 3043. On the other hand, if you search for the term solid earthing, it is mentioned in more classes, 25.3.2, 27.5.1 and 39.3. So Indian Standard 3043 more prefers to use the term solid earthing rather than effective earthing. And resistance earthing, it is also, if you search for resistance earthing, Indian Standard 3043 mentions resistance earthing in various classes, 25.3.2, 29.3.1, 33.2, 33.3 and 39.1. So the Indian Standard, if you say IS 3043, does not per se explain effective earthing or explain non-effective earthing. It says solid earthing and resistance earthing. Then if you see IS 732, the next important standard, here also in one class, one particular class, it mentions effectively earthed system as a passing comment, effectively earthed high voltage system. Here it says neutral is connected directly or a very, very low impedance where earth faults are cleared in a very quick time. So to be qualified as an effectively earthed system, the earth fault impedance should be very, very negligible. That is what is said here. And in one more place, if you see National Electric Code 2023, there is also a couple of mentions about effectively earthed system in a particular annexer to a particular section at part 13 section 1. It mentions effectively earthed system. So in a different approach, it is mentioned in a chapter on surge protected devices, but definitely a mention of effectively earthed system does appear in NEC also. And one more place in NEC, Annex C to part 7, it is for generators. It says generator equipment, electrical equipment shall be effectively earthed. So, but per se, no standard in India has precisely explained what is effective earthing, what is non-effective earthing. So, if that is the case, again, NEC mentions solid earthing in many places rather than effective earthing. It also mentions solid earthing in a couple of classes. Now, if this is the case, what is the origin? Where is the term effective earthing and non-effective earthing originate from? How do people talk about this terminologies, effective earthing and non-effective earthing. In fact, it is one more popular book called the IEEE Green Book. In IEEE Green Book, there is a mention, IEEE 142, IEEE 142, that is popularly known as the Green Book, that is IEEE recommended practice for grounding industrial and commercial power system. It precisely mentions what is effective earthing. Effective earthing, they say, a system of earthing in which the zero sequence reactance to positive sequence reactance ratio is less than 3. That means the reactance, earth fault, zero sequence reactance or earth fault loop reactance is very less. Similarly, the resistance, zero sequence resistance to positive sequence resistance. If you see the resistance in the earth path, the zero sequence path, it is also not greater than 1. At the maximum, it is equal to the system positive sequence reactance, or many times it is much lesser. So to be qualified as effectively earthed system, these two conditions are must. The ratio of x0 by x1 should be less than 3, and the ratio of r0 by x1 is less than 1. So this is the proper definition of effectively earthed system, but unfortunately this appears in American standard, IEEE standard, not any Indian standard. But Indian standard does say in class 27.5.1 there is a mention in a solidly earthed system, whatever the qualification defined for effectively earthed system in IEEE is satisfied in solidly earthed system. In this class, the IS 3043 very clearly says, in case of solidly earthed system, the ratio x0 by x1 is limited to less than 3, and the return path, the earth return path is reasonably low. That means it also indirectly says r0 by x1 is less than 1. So going by this definition, it matches with the definition given in IEEE 142, the Green Book. So we can say all solidly earthed systems are effectively earthed systems, and which are not, which does not satisfy this condition, x0 by x1 is greater than 3 or r0 by x1 is greater than 1, they automatically become non-effectively earthed system. So this is the definition I wanted to give. One more friend of mine from Kerala has asked me to explain this in the beginning itself. So this is the definition I could find in Green Book. Now, just in a layman's language, what is solid earthing? The neutral point of transformer or generator are connected directly through an adequate ground connection. Adequate in the sense the sizing, thermal sizing, dynamic sizing, all those things, in which no impedance has been intentionally inserted. We do not add any resistance, we do not add any reactance in the neutral to ground path. So it is as direct as possible. A solid conductor is connected between neutral and earth, like this in this figure. So you can see in the neutral to ground path, the black color bus bar is the neutral bar, and to earth there is no intentional earth, any resistance or reactance is not added intentionally. We are not adding. Please recall, when we discussed unearthed system, we said that though it is unearthed system, there is a capacitive coupling existing between each phase and the earth, and between phases also. But since between interface capacitance are not involving earth, that is not the point of discussion in this webinar. So we are interested in the capacitive coupling between phase and the earth only. Since R phase has got earthed, R phase capacitance gets short circuited because the top plate of the capacitor will also be in R phase potential, the bottom plate will also be in R phase potential, so it is bypassed. So there are two capacitances, Y phase capacitance and blue phase capacitance will also discharge into the fault. Similarly, since there is a low impedance path between the earth and the neutral, so definitely current will try to flow, fault current will try to flow into the neutral, back to the neutral from the faulted zone. So if you can draw a vector diagram, you can see IRY is a capacitive current, IRY is the Y phase capacitive current, IRB is the blue phase capacitive current feeding into the fault. The neutral and ground are solidly connected. Now R phase, since R phase is grounded, there is no RN voltage. Now if you see, the capacitive current itself is the vector sum of IRY and IRB, which has become IC now. Now there is, apart from this capacitive current, since if it is ungrounded system, only this current would be the fault current. But since we are solidly grounding, there is another component, very big component. Huge fault current will be there. So reactive component will be there. This component, this major fault current and this negligible capacitive current will vectorially add to give you the effective fault current. Many times this is compared to this current, this is almost negligible, but nevertheless for academic interest I have drawn this vector diagram. So the fault current will be a vector sum of fault through the grounded neutral and the capacitive discharge currents. But the current is very huge. Now, what will be the value of this current? In a solidly grounded system, if single line to earth fault happens, what will be the value of this current? There is a mention in the standard IS 3043 in class 39. The magnitude of the current that will flow in the event of a single line to earth fault on an earthed system is determined by the impedance from the source to the fault plus the impedance of the earth return path, including if you go for opting for transformer earthing or resistance earthing or reactance earthing, if any impedance are included, you have to add that. But in solid earthing, these three are neglected. Impedance of earthing, transformer, resistance, reactance are neglected. So it is always the impedance, fault impedance from the source to the fault plus the earth return path. It also makes a reference to cross reference to refer to IS 13234. It is the guide for calculating short circuit currents, Indian standard guide for calculating short circuit currents. If you see the IS 13234, it does give a formula. It gives a formula. If you can see, the formula is single phase earth fault current is called IK1 double dash is equal to √3 CUN divided by 2 Z1 plus Z0. That is, C is a constant. It may vary from 0.9 to 1.1 depending upon the system conditions, voltage fluctuations. 0.9 to 1.1. UN is a system voltage, line to line voltage, line to neutral voltage. Z1 is a system positive sequence impedance. Generally, the IS 13234 says for all static equipment, that is lines, reactors, transformers, non-rotating equipment, Z1 is equal to Z2. Actually, the formula is Z1 plus Z2 plus Z0. Generally, the IS 13234 says Z1 is equal to Z2 for all static equipment. So they have added both and mentioned 2 Z1 and plus the zero sequence impedance in the system. So generally, also many times the Z0 is almost equal to Z1 in many cases, except in some transformers they will give the value of zero sequence impedance. From the manufacturer you can collect. In one more class, the IS clearly says, assuming that Z0 is also equal to somewhere close to Z1 and Z2, this formula becomes 3Z1. That means UN by √3 Z. UN by √3 is U phase, V phase. U phase by √3, U phase by Z is symmetrical short circuit fault current formula. So the Indian standard also very clearly mentions in solidly earthed system, the ground fault current can be of the order of 3-phase symmetrical short circuit current. That means when there is a 3-phase fault in the system, what will be the fault current? The single phase line to ground fault current, earth fault current will be equal to the 3-phase fault current. That very clearly mentioned in the Indian standard. Similarly, the advantage, if you see the look into the advantages of solidly grounded system, Indian standard itself documents the advantages. In a number of systems, greater service continuity may be obtained with earthed neutral system because if you recall, last time we discussed the advantage, one of the important advantages of the unearthed system was service continuity, because there will not be significant fault current flow because the unearthed system, the neutral is isolated from ground, there is no return path. So there will not be any significant fault current flowing. So the system will not get disconnected because there is no sensing of the ground fault current, there is no tripping of the breaker. So there will not be any service isolation, service discontinuity will not be there. This was thought to be the biggest advantage of ungrounded systems or unearthed systems. But subsequently, we have also seen that sooner than later, the single line to ground fault will culminate into a double line to ground fault. The second line will be stressed, the second line insulation will be stressed, and sooner than later, second line also will short circuit with earth. So the LG fault will become a LLG fault. LLG fault, the magnitude is very high. So definitely your fuse or breaker will blow, will trip, isolate the faulty zone. So the advantage of service continuity is definitely lost. So whereas in solidly earthed system, by perfectly doing coordination, you can see that only the faulted portion is affected, only the faulted zone is isolated, healthy portions are not affected. Since the current detection is possible here, current detection is possible, you can always provide a current transformer and a protection relay, earth fault relay. You can always isolate the faulty portion only. The healthy portions can remain in service, or service continuity can be guaranteed. And similarly, we have also seen in ungrounded system, there are chances of restriking faults, because once the one phase gets grounded, the other two healthy phases with respect to earth, the voltage shoots up by 1.732 times, root 3 times. So there is a voltage stress. So there are always chances of arcing fault, repeated or multiple ground fault. As I told you, the second phase insulation with the ground is stressed, and sooner than later a second fault appears, maybe a third fault. So there are chances of multiple ground faults in ungrounded system, whereas in earthed neutral system that is not possible, because even when one phase grounded, the ground potential appears in the phase rather than phase potential appearing in the other two phases. The other two phases are always kept at a neutral potential, so they are not stressed. Also, the earth fault current is very significant, so that there can be quickest possible isolation, so that the healthier system are not stressed. This is also documented in IS 3043 as the advantage of solidly earthed system. Then arcing fault. There are, as I said, these faults can also develop arcs, repeated arcs. This can be arcing fault, arc fault, you know, today that is also gaining momentum and interest in the industry. Arc flash protection, arc flash hazard, arc flash studies, all those things are there. So in unearthed system, there are chances of, you know, repeated arcing faults and arc flash hazards could be there. The standard says in solidly earthed system, so always to avoid arc flash hazards, quickest possible arc detection and isolation are necessary. So today you have got very quick arc flash detection sensors, which operate within 10 milliseconds also, I am told. Within 10 milliseconds, the sensor can detect and isolate, give a trip command to the breaker. So quickest detection is warranted in arc fault hazards. So in solidly earthed system, it is possible to achieve a quick detection and quick isolation, because the current involved is huge. When the current involved is huge, you can always detect and protect with a suitable relay. So in solidly grounded system, one more advantage is arc flash hazards are minimized because of quick detection and isolation. And transient buildup, voltage buildup, neutral, we saw that the neutral to ground voltage will be raised to phase voltage times, because in ungrounded system, ground, whenever one phase gets grounded, ground rises to the particular phase potential, neutral is kept at zero potential. So neutral and ground, there is a voltage buildup. The neutral will no more be at 0 volt, ground volt. So there will be voltage buildup in the neutral. So we called this neutral shift. So when you do solid earth, when you connect the neutral with solidly with the ground, it never happens. The ground is always kept at neutral potential, neutral is always kept at ground potential. So there is no chance of any transient over voltages happening in the system, because we saw that transient over voltages will happen in ungrounded system. We saw that. We saw with a lot of diagrams and explanations I have given how this rise to calculations and formula in how transient voltage buildup will happen in unearthed system. In solidly grounded system, the chances of a transient voltage buildup are very negligible. And as we have seen, the ground fault current is substantial. Accurate detection and location of earth fault is possible. Transient over voltage is minimum. The neutral shift is negligible. Equipment, normally the insulation sizing, since you are solidly grounding the neutral, all the phase to earth insulation downstream of such a network can be insulated for phase to neutral voltage only. So the insulation cost comes down greatly. Similarly, since a single phase line to earth fault current is equal to the three phase symmetrical short circuit current, you do not need any special sensitive earth fault protection devices. The current involved is in kiloampere generally. So when the current involved is in kiloamperes, any short circuit protective device in your system, like a HRC fuse or an instantaneous overcurrent relay you have provided, the 50 relay, any short circuit relay you provide in your system will act for this current and will isolate the fault very, very quickly. If you take a case of a fuse, for severe faults, the fuse operating time is less than 10 milliseconds. Even sometimes good fuses are there which operate below the current peak, 5 milliseconds they operate. So the fault isolation can be very, very quick before it harms a person or harms a system or installation. Isolation is possible. So the protection can be something like this. You do not need, even in the system, if that happens to be an earth fault, you don't need an earth fault relay even, because the current involved is in kiloampere. The fault feeding phase will also sense the kiloampere current, and any relay or fuse you provide in the phase itself will open the breaker or fuse will blow out, thus isolating the faulty zone. Very quick time it will do. Suppose you need, still you say that you need a sensitive, better earth fault protection, sensitive earth fault protection. Even you can provide a earth fault relay in the residual path. This is the most common practice in industries. People do 3 overcurrent elements and 1 earth fault element. You can provide a earth fault element with a sensitivity of say 10 to 40% or 20 to 80%. So you can provide. Suppose if you don't have a phase relay, if the current any earth fault sensitivity will be more than 100%, because phase fault relays are set to 100% or more. Here, see, if you want a finer setting, you go for a residual connected earth fault relay, where you can set as low as 10% of the CT primary rating. So better sensitive protection is also possible, made possible here. And the lightning arrestor selection, if you call the lightning arrestor selection, depends upon the method of system earthing. There is something called a ground fault factor in the formula for calculating the rated voltage of lightning arrestor. There is a factor called ground fault factor or earth fault factor or coefficient of earthing, which is 0.8 in the case of solid earthing. So the lightning arrestor can be rated highest system voltage into factor of earthing. So you can always go for a lesser rated voltage lightning arrestor, the cost and size will reduce. Similarly, if you see the PT standard 61869 IEC or IS 162273, if you see, there is a factor called over voltage factor for voltage transformers. In an ungrounded system, the over voltage factor is 1.9 for 8 hours, whereas in here 1.5 for 30 seconds is more than sufficient. The standard says, PT standard says, in a solidly grounded system, it is 1.5 times for 30 seconds. Why? Because since the current can be detected and the fault can be isolated, a duration of 30 seconds is more than sufficient. So when you reduce the voltage factor of the VT size and the cost reduces. Similarly, if you see the specification for cable, they say UE cable and E cable, unearthed cable and earthed cable. So if you go for a earthed system cable, the cost comes down, cable cost comes down. Suppose you say 11 kV UE or 11 kV E. In fact, 11 kV E cable is actually a 22 kV UE cable. So for 11 kV, so when you use for a system unearthed cable, you go for actually the next higher size voltage size cable. So the earthed cables, if you go for earthed grade cables, they are cheaper actually. Or putting the other way around, 6.35 kV unearthed cable can be used for 11 kV earthed system. So for 11 kV earthed system, in fact, you are using a 6.6 kV cable. So that is the advantage of solidly grounded system. The cost comes down. You know, in any industry, the cost of cables is industrial project. The cost of cables is very significant. So the solid earthing brings down the cost of the cables significantly. And disadvantages. And 1 minute, one more advantage. Disadvantage, if you see, all the problems associated with high fault current. Yes, high fault current means, you know, the thermal damage, the I squared T, thermal damage. So all the touch voltage will increase. So whatever the high current related problems will always be there in solidly earthed system, because the current is very high. And because the current is very high, damages are high and disturbances will be there. And the system should be designed for the high value of fault current, the earthing conductor, the earth fault, interconnecting equipotential bonding conductor, earthing conductor, protective conductor, everything has to be sized for the high value of earth fault current. And the faulty feeder compared to ungrounded system. In ungrounded system, faulty feeder will not be disconnected. If you compare, make a one-to-one comparison, service continuity or the faulty feeder will not be there because it gets tripped. And ground fault current is high if you have rotating machines. If you have rotating machines in your system and the fault happens within the rotating machine, core and windings are involved. If the core is involved, so generator and motor, if the fault happens, earth fault happens inside the machine and solid earthing, high current will flow. So there are chances of core damage in the rotating machine. Similarly, when high fault current is there, the touch voltages are also very high. So, it is again a grid resistance into the fault current. So, if fault current is very high, the voltage, touch voltage hazard is also increased. And in IS 3043 also, in one place it is documented, relatively high fault current associated solidly earthed system may present a hazard to workers from exposure to hot arc products and flying molten metal. So it also acknowledges the high fault current is a disadvantage. Of course, there is a second part to this class. It is said that most of the industrial systems are metal enclosed switchgear. So maybe it need not, this class may not be taken very seriously because the metal clad switchgear and metal enclosed switchgear are generally tested for internal piston. So they say, but definitely the disadvantage is recorded in IS 3043 also. So the protection, suppose how to implement a earth fault protection in a solidly grounded system. Generally, as I said, you definitely do not need a separate earth fault relay. The phase fault relays themselves will sense this high current and trip. But if you want a very sensitive protection than that is offered by the conventional overcurrent relays or short circuit relays, you can always go for a 51N element, delayed earth fault protection element, or you can go for a instantaneous 50N element, like we have seen in that scheme. You can go for either 51N or 50N protection is possible because current is detectable. So application, the recently released CEA regulation 2023. If you read the regulation 43, 1, 2 and 13, in here it is mentioned that the neutrals of every generator and transformer must be connected to the nearest earth electrode or earth connection, earth grid, not less than 2 separate and distinct connections. So it mentions that since there is no mention of the word impedance, it implies that they have to be connected solidly. This is for voltages more than 650 volt, that is high voltage system. Same CEA rule 52 says that the neutral point of every generator and transformer shall be earthed by connecting it to the earthing system by not less than 2 separate and distinct connections. Yes, if you see the second para, it gives you a exit class for generator only. If necessary, the neutral point of a generator may be connected to an impedance, which mentions that the above point, the neutral point of every generator and transformer shall be earthed, is meaning solid earthing only, because for resistance earthing a separate exit class is given. So the main rule 52 says that the neutral point of every generator and transformer must be earthed directly or solidly. This is also documented in CEA regulation, latest CEA regulation also. Then again 54, same rule, sub rule regulation 4 says, 50 sub regulation 4 says, single phase system, if you happen to have a single phase system, high voltage system above 650 volt, they also have to be effectively earthed. As we have seen earlier, effective earthing means solid earthing. This is also documented in CEA regulation. And in IS 3043 also 27.1.2 it says the neutral of the transformer should be connected to the earth electrode by duplicate connection. That means solid connections. Then NEC, National Electric Code 2023, Section 18, Class 5.1, Part 1. Earthing system above 230 volts should be designed as protective multiple earthing system with a separate protective conductor TNS. If you recall, first letter is the method of system earthing. T means terra, terra means natural earth in French. So, IS 3043 also says that any system above 230 volt must be solidly earthed. The first letter of the network classification refers to how your system is earthed. The system neutral is earthed. T means terra. That means the neutral should be connected to terra. Terra means as close to earth potential as possible. That is solidly earthed. So it also further explains that in a protective multiple earthing system, neutral of the supply transformer and the non-current carrying metal parts in the system are interconnected by a common earth grid. That means they are connected, the transformer neutral is connected solidly to the earth grid. So there is no question, it must be solidly grounded. Then the subsequent class, 5.2 class in NEC says, in TNS system with protective multiple earthing, the neutral of the source, let us for a moment forget the equipment earthing, the neutral of the source may be a transformer, the source may be a generator, the neutral of the source solidly connected to the main earthing terminal and the earthing grid. That means even in IS 3043 for systems above 230 volt, solid earthing is recommended. Solid earthing is mandated actually. So, okay, having said that, okay, solid earthing has got so many advantages. Solid earthing is the best. All the rules talk about solid earthing, rules mandate solid earthing, standards mandate solid earthing, codes mandate solid earthing. Then what is the purpose of having resistance earthing? Why should one go for resistance earthing? Or where should one go for resistance earthing? Now, in resistance earthing, the neutral of the transformer or generator are grounded through an impedance. The principal element of that impedance is resistance. So, where to use this resistance earthing? This method is used when the earth fault current is to be restricted. If you solidly earth, the earth fault current is unrestricted, there will be huge flow of earth fault current. If one wants to restrict the earth fault current, one may have to go for resistance earthing. The case in point is medium voltage generators. That is medium voltage. Here I am talking about above 1000 volt up to 35 kV. So high generators of above 1.1 kV, because anyhow below 1.1 kV you must solidly earth the generator, or if multiple generators are there, impedance earthing or neutral switching, that is we will discuss in a separate session. But as far as now concerned, here resistance earthing is mostly practiced for medium voltage generators. The schematic is something like this. Compared to the solid earthing drawing seen, here you can see a black body between the neutral and the earth. The black rectangle is the neutral resistor, ground resistor. RG is the NGR, neutral grounding resistor. So here also there will be a capacitive current formation, but that is again capacitive current contribution will be there. But as seen, it is almost negligible. It is less than 5 ampere or less than 5 ampere in the case of LV system and less than 25 ampere in the case of medium voltage and high voltage systems. So here a resistor is connected intentionally between the neutral and the earth. The purpose is to limit the earth fault current. The reason why you have to limit the earth fault current, the major reason in rotating electrical machines like motors and generator, if the earth fault current is very high, as in the case of solid earthing, the core damage will be very high. To limit the damage to the core, if you ask, the machine manufacturer will give you a core damage curve. A limited ground fault current is allowed. This is given in the form of a core damage curve. So this core damage curve will look something like this. This I have taken from a motor manufacturer's catalog data sheet. So you can see x-axis is seconds, y-axis is current. So how much current it can tolerate for how long? You can get this data from the generator manufacturer or the motor manufacturer. You can demand, please give me the core damage curve of your machine. They will give. So if you see, typically 25 ampere 1 second is tolerated. If you see, this is the 25 ampere and 1 second. This is the green zone. So negligible burning is seen. So generally this is 20, this is 30, this is 25 ampere for 1 second. So generally 25 ampere for 1 second is the core damage limiting value. This is used as the guideline in selecting NGR generally. Selecting NGR and setting up the stator earth fault relays in generator protection schemes. Now, why should you worry about core damage? If you recall, winding damage, suppose your winding insulation burns or winding gets damaged, in big cities, at least even including tier 2 towns, you will have a rewinder, a good rewinder, or the rewinder authorized by the equipment manufacturer, motor manufacturer, generator manufacturer will be available in a nearby town or city. So you can always take the damaged machine to him and he will be able to rewind it and give it to you. Authorized rewinder or a good rewinder, he can do the job. The machine can be brought back to service very quickly if it is a winding damage. But in case of core damage, the local rewinder does not have the expertise or the facility to repair the core. Generally, any core damage, the machine must be sent back to the manufacturer. So the machine manufacturer also may not take up the repair job immediately. So he will give priority to production. So as and when his staff are say, maybe he can allot his staff for repair work, he will allot them for repair work. So generally, even thinking that they have a dedicated service team for attending, the transit time from the industry or from your facility to the manufacturer's works, time taken for repair, core damage, repair there, and time taken to transit time back. So if you see the core damage always takes prolonged periods of downtime in the factory and loss of production. So one must try to avoid this situation. One must try to avoid core damages. How to do it? It can be done by resistance earthing only. Then taking forward, rotating electrical machines are not present in 22 kV onwards. Less than 22 kV we have seen generators, 24 kV generators are there, 11 kV up to 11 kV motors are there. Maybe I am not come across any 22 kV motor access, whereas 22 kV generators I have seen. Motors are there right up to 11 kV motors are there, 3.3, 6.6 and 11 kV motors are available. So rotating machines are present in the network right up to 22 kV. So if rotating machines are present in the system, you go for, if the rotating machines are not present, you go for solid earthing to gain the advantages of solid earthing. The biggest disadvantage of solid earthing is core damage curve, but if you don't have rotating electrical machines, you need not worry much about that. But if you have rotating electrical machines, you must go for resistance earthing. EHV level beyond 66 kV, solid grounding is adopted. Why? Because the cost of insulation, is very significant as you go higher up in the voltage, because the phase voltage is also increases. Suppose if you take a 66 kV system, the phase insulation is 66 by root 3, somewhere around, let us say 30 kV, whereas the line insulation is 66 kV. So if you solidly ground, you can design your system, lightning arrestor, PT, everything for 66 kV by root 3 only. If you go for non-effectively earthed system or impedance earthed system, you must design everything for full line voltage. So the cost difference between 60 kV earthing and 30 kV earthing is very huge. Even if you go higher, it is still higher. Say 110 kV or 110 by root 3 or 132 by 132 by root 3 or 220 by root 3, 400. So if you go higher up and higher up, there is big advantage in gaining cost savings in insulation costs if you go for solid grounding. So definitely, this is a very significant point in going for solid grounding in EHV system. Second thing is, yes, current is a fault detection is a criteria, but generally all EHV systems will have a unit protection. It is a mandatory. It will have unit protection like differential or restricted earth fault or bus differential will be there. So these systems are instantaneous. You cannot build up any intentional time delay in this unit protection schemes. They are capable of clearing the fault within 100 millisecond or 5 cycles. So fault shall not be kept in the system for longer period because you have a dedicated unit protection scheme. This is mandatory for EHV. So generally EHV people go for solid earthing. The advantages of solid earthing outweigh the disadvantages, so they go for solid earthing. So if rotating machines are present in 3.3 kV, 6.6 kV, 11 kV, the systems are grounded through reactor or resistor to limit the earth fault current. If rotating machines are not present in this voltage level, these systems can be solidly grounded. Now a big question comes. If you want to protect the rotating machine, if you see the population of rotating machine, the population of rotating machines is very high in low voltage only. That is below 1000 volt, 415 volt system. But in 415 volt system, by rule, you must solidly earth. If you solidly earth the neutral, your motor is going to get damaged. Your motors are going to get damaged. So the biggest question is that low voltage system. What about low voltage system where the maximum number of rotating electrical machines are in use? But by mandate, by rules, by codes, you cannot resistance impedance earth the low voltage neutral. Low voltage neutral by IS 3043, by CEA regulation, by NEC, you must solidly earth the low voltage neutral. In case of LV system, though a large population of rotating machines are present, the system is solidly grounded to conform to the regulations and standards and codes. Since LV system is also handled by general public, for safety reason, solid grounding is mandated, because in solid grounding, you do not need a dedicated earth leakage relay or ELCB or RCCB. The overcurrent device or the short circuit device itself will blow and protect, open and protect. If not, maybe human protection people may not mind. At least to safeguard their equipment, anybody will go for a fuse or a breaker to safeguard their equipment. So in solidly grounded system, the device, such a device provided to protect the equipment will automatically isolate the fault and protect the people also. So that is the reason for going for recommending and mandating solid earthing for LV system. Sufficient ground fault current is allowed to flow in solid grounding so that SCPD can operate and clear the fault. But since you are allowing the high fault current, core damage, if the fault happens within the machine core also will get damaged. But then, how do you comply with the regulation? Still protect your low voltage rotating electrical machinery from core damages due to high earth fault current. So you have to have the cake and eat it too. Since many rotating machines are present at the low voltage level, it may be worth considering resistance grounded system even at this level to limit the earth fault current. A very simple solution would be bus segregation. The low voltage bus can be segregated into those supplying rotating machines with the resistance grounded system and those supplying loads that are handled by common non-electrical people or common public like lighting and heaters. That must be solidly grounded. Something like this. You put your two transformers. One will be solidly earthed, which will be connected to lighting and heater load. One will be connected to motor loads with the resistance grounding. This way you can follow the rules and you can protect your rotating machines also. Other reasons why you go for resistance earthing: reduce the burning and melting in electrical equipment. Solid grounding, we said, very high current. In resistance grounding, you are limiting the earth fault current. So that much burning and melting is minimized. Similarly, mechanical stresses are reduced. The forces developed during short circuit, electromechanical forces or electrodynamic forces developed during short circuit, the formula is force is directly proportional to square of the peak current. So if you reduce, provide a resistance, the RMS current reduces, fault current reduces, the peak fault current reduces, the force reduces, the stresses reduce. Then arcing faults can be minimized because you are limiting the current. Arcing faults can be minimized. Restriking fault or arcing fault can be minimized. Again, there are two sub-classifications of resistance grounding. One is called high resistance grounding, other is called low resistance grounding. Again, I am taking reference from the Green Book. There is only a reference in Green Book. High resistance grounded system is designed to limit the ground fault current to a value that can be allowed to flow for an extended period of time, still meeting the criteria. R0 is the system earth fault resistance, loop resistance is less than the system zero sequence capacitance, so that transient voltages are reduced. The ground fault current generally limited to less than 10 ampere. as I said, core damage minimization. So in high resistance grounded system, the ground fault current is limited to about 10 to 15 ampere. This is the general guideline. But generally you go as per the core damage curve given by the rotating machine manufacturer in your system. Go by the guideline given by the equipment manufacturer. So suppose you go for a 11 kV system, the ground fault current should be limited to 10 ampere. The value of NGR generally phase voltage divided by the intended earth fault current, 11,000 by root 3 divided by 10. If you provide a 635 ohm resistor in the neutral to ground path, the fault current will be limited to 10 ampere, like this. Now, one method is directly provide a 635 ohm resistor rated for 6.35 kV. 6.35 kV, 635 ohm resistor directly in the neutral circuit. This is again a costly affair. 635 ohm very resistance value, and also it should be insulated for 6.35 kV. But if you use a small transformer, NGT, neutral grounding transformer, and provide a very small resistance in the secondary of the neutral grounding transformer, that will reflect as a very high resistance in the primary of the transformer. This is the basic transformation theory. This uses the elementary fact that an impedance connected to the secondary side of the transformer or LV side of the transformer gets reflected as impedance multiplied by square of the turns ratio on the high voltage side, where TR is the turns ratio. I have given some example. In the first left hand side example, I am connecting a very high resistance, 1000 ohm resistance rated for 11 kV. Now secondary current, if you see, 240 by 5 is 48 ampere. The secondary resistance, 5 ohm resistance reflected on the primary side will be 10 kilo ohms, so approximately 10 kilo ohms multiplied by the turns ratio, square of the turns ratio. This is in parallel with the 1000 ohm resistance. So the net resistance will be 930 ohms on the primary side. The resultant fault current, the current in the primary side will be 12 ampere. Suppose if you provide a 1000 ohm resistance in the HT side, 11 kV side, rated for 11 kV, 11 kV 1000 ohm resistor will result in a fault current of 12 ampere. Whereas if you see the diagram on the right hand side, I am connecting only a 0.476 ohm 240 volt resistor on the secondary side. This also results in 12 ampere fault current on the primary side. So the advantage is you connect a NGT, provide a very small value resistor across the secondary terminals of the NGT. You get a same effect as connecting a very high value resistor on the primary side. So like this, instead of going for a direct resistance, high voltage, high current resistor or high value resistor, you go for a NGT, neutral grounding transformer, secondary of which is connected to a very low value resistor. Now here for the same 10 ampere, we had to connect a 635 ohm 6.35 kV rated resistor in case of directly connecting a resistor in the neutral to ground path. Here if you provide a NGT, the NGT ratio is 11 kV by root 3 by 240 volt. Turns ratio of the NGT is 26.5. The value of resistor to be connected on the LV side, you connect only a 0.9 ohm resistor on the 240 volt side of the NGT. It will be reflected as 635 ohms on the HT side of the NGT, 6.3 kV side of the NGT. You will get the same 10 ampere current limitation on the HT side. So you see the biggest advantage, a low voltage, low value resistance becomes very economical and easy to handle also. Also, since you have a resistor and a current is flowing, you will have a voltage drop. So when there will be a voltage across this secondary, only when there is a current flow in the primary of the NGT. When there will be primary current flow in the NGT, only when there is a system earth fault. So you connect a voltage relay, 64 ND or neutral displacement relay across the resistor. So whenever there is a fault, current will flow in the primary of the NGT. Whenever current flows in the primary of the NGT, it will set a flux in the secondary. The secondary winding will cut that flux and EMF is induced in the secondary. This EMF is detected by the 64 ND and you can allow tripping of the system. But the problem is you cannot achieve current based protection. The problem is earth fault relays, conventional earth fault relays cannot be connected in a residual circuit as the fault current magnitude is very less compared to the rated current of the feeder. We will take an example. I am having a feeder of 800 ampere, CT ratio 800 by 1 ampere. The earth fault relay setting is 10% of 800 ampere, that is 80 ampere. Suppose I provide this relay in this system, it will never trip because the current is only 10 ampere. There is no point in providing a relay in the first place. You can go for a CBCT, suppose because the current is less than 10 ampere, you go for a sensitive CBCT, earth leakage relay or RCCB or earth leakage relay with the CBCT, you go and set the setting below 10 amperes. Very sensitive earth fault relay where the primary earth fault current as low as 2 ampere can be detected. But again, you have to be very careful about this selection because it can also react for some system unbalances during switching on of transformer, during switching on of motors, cables, some zero sequence element may be present during switching on. At that time, they should not trip. So there must be a time delay also inbuilt in such a protection. Then low resistance grounding. In low resistance grounding, we are connecting a resistance directly, very low value resistor directly in the ground, neutral to ground part. Here, since the current is significant, you can connect a neutral CT and connect a current operated relay also. In low resistance grounded system, the earth fault current is limited to about 400 ampere. Here, generally, what is the criteria? The criteria is limit to the fault current to the full load rated current of the transformer. Where should I select 400? Why not 200? Why not 400? Why not 1000? The general guideline is limit the current to the rated full load current of the transformer or generator. Mind you, generator always the core damage point you have to keep in mind. But if core damage is you are ready to ignore or the core damage value is higher, you can also go for rated full load current of the generator. In IEEE Green Book, again there is a definition for low resistance grounded system. The permits a higher ground fault current to flow to obtain sufficient current for selective relay operation. Usually meets the criteria resistance R0 to X0. Zero sequence resistance to zero sequence reactance ratio is less than or equal to 2. Ground fault current generally is between 100 ampere and 1000 ampere. This is the definition given in the Green Book. So on a 11 kV system, suppose I want to limit the earth fault current to 400 ampere. So 11 kV by root 3, 6.35 kV divided by 400. I have to connect a 16 ohm resistor. Voltage rating will be 6.35 kV, 16 ohm resistor directly connected across the neutral to ground part like this. Now current is, since the current is 400 ampere or 100 ampere, more than 100 ampere, you can always provide a current transformer in the neutral to ground part, provide a relay. It can be an IDMT relay or it can be an instantaneous relay depending upon your coordination requirement. You can select an appropriate relay and connect across the NCT. But here, since you are allowing a higher current, the core damage, probability of core damage is much higher. So earth fault relay can be, since current is very significant and detectable, you can go for a residually connected earth fault relay also, like this. 100 ampere or 400 ampere, any current above 100 ampere can be detected by this scheme also. So you can go for a residually connected like a conventional today feeder protection relays are available with 3 overcurrent element or earth fault element. You can connect like this. Advantage of resistance grounding system: it is a compromise between low fault current and it is a compromise between unearthed system and solidly earthed system. In solidly earthed system, fault current is high, that is overcome by low fault current. In unearthed system, because of resonance between reactance and system capacitance, over voltages are possible. Here the zero sequence path is made resistive, so there are no chances of resonation. So over voltages are reduced. The other day we have seen what happens if the circuit is earth fault loop circuit is resistive. The maximum current that can go in such a case is root 2V. However, system is designed for tolerating a peak voltage of root 2V. So there is no transient over voltage. So it is a very good compromise between solidly grounded system and totally ungrounded system. The protection units are simple and selective. Fault current is limited. Disadvantages in low resistance grounded system or a high resistance grounded system with a very sensitive earth fault relay or a neutral displacement relay, service continuity of the faulted feeder is downgraded. That means faulted feeder gets tripped compared to ungrounded system. Earth fault must be cleared as soon as they occur. Otherwise, the same disadvantage, because the ground always rises to faulted phase. The higher the voltage and the higher the current to be limited, the limitation higher, the lower value of earth fault current, the higher will be the cost of the resistor. Ohmic value increases, voltage grade increases, so the cost will be more. Protection. In high resistance grounding, a separate sensitive earth fault protection unit operated by a CBCT or by zero sequence current sensing relay should be provided, as the phase relays will not sense low earth fault current. In low resistance grounding, the earth fault relay may be connected either in the neutral earthing path or in the residual circuit of the phase over current CTs. We have seen both. So it is quite simple, possible to detect and isolate. Applications: medium voltage distribution, public medium voltage distribution system, industrial medium voltage distribution system, where you want to reduce the fault current. Generator, mainly for generator applications, ME medium voltage generators and transformers. In fact, this is very popular in United States. So they always they publish a lot of guidelines and articles on neutral grounding, resistance grounding of neutrals. So that is that in this webinar. Maybe I will join you in a next webinar and we will continue with reactance earthing. I am open to questions now.
Yes, thank you very much, sir. It was a nice session. Hope we also had a lot of participants today. As usual, it crossed the 200 or much more were there.
Yes, sir.
Now we have few questions. There were some questions on the chat box. Anyway, chat box questions we may not be considering. So in the Q&A, we have the first question. This is related to resistance earthing in mines, where the current has to be limited to less than 750 milliampere, and how the protection is achieved, the disconnection is achieved, is the question.
You have to have a earth leakage relay, sir.
Yeah.
I am not very, I will just have to refer. There is a definite session in NEC for mines, no?
Yes,
and
there is for
CE
yes.
also mines protection is there. Generally, if you have a 750 milliampere earth leakage current, you always go for earth leakage relay, which has definitely got a 750 milliampere setting, and that relay's output contact you connect to your VCB, possible. But more often than not, I understand that mines, they follow unearthed system. I understand, I think, because the fault current, all those issues will be there. So maybe I am some people may correct me, but as far as my understanding goes, they would prefer to go for ungrounded system or highly impedance grounded systems.
Correct, because the idea is to reduce the fault current.
Yes.
So that is
why separate earthing is required for instrument and electrical, while all earthing has the same potential? The very concept is, I would say, wrong. Mr. Gaurav Mishra's question. Please go please study IEEE 1100. There is a publication called IEEE 1100, recommended practice for grounding sensitive electronic equipment. It does not recommend isolated grounding for sensitive electronic equipment or instrumentation equipment. This is a myth we are having. It should not be isolated. It should be interconnected with the grid. Ultimately, to the plant grid, it should be interconnected. That is the guideline given. That is the only known standard for grounding of sensitive electronic equipment is IEEE 1100, which does not advocate isolated earthing.
Yes, actually, I would like to add here, there are some IEC standard as well, 30129, ISO. It's an ISO, ISO 30129. It's a ISO IEC. It's a earthing of all the sensitive electronics. So basically now connecting both power protective earthing and the functional earthing to the earth grid is already out. Both has to be connected to MET, to the main earth bar. These
Yes.
clarifications are also there in IS 732 and IS in the NEC. So some clauses were given. So basically this making the separate is a myth, as Shivakumar sir told. Sir, shall I take the second question from the top?
Yes, sir.
Amresh Prusti, there is a 3.3 kV bar 415 volt transformer. The secondary is NGR grounded, output voltage measurement showing discrepancy in phase to earth voltage, while bypassing the NGR voltage between phase to earth is balanced. What could be the reason?
First of all, 415 volt transformer neutral is not supposed to be NGR grounded. First of all, going by IS 3043, going by NEC, going by CEA regulation, 415 volt neutral must never be NGR grounded. Okay, maybe you have taken special permission, you have put a NGR grounding. Please send me the SLD. I will study and give you the solution.
Yes, so Mr. Amresh, you have the phone number of Mr. Shivakumar. You can send to him. Mr. Shivakumar will
Or
help
you can even post in NFE WhatsApp group. I will try to address it.
Yes, I think that is the best way. So we
Yeah,
have a
WhatsApp,
group.
NFE WhatsApp group you can post. I will definitely try to address your question.
Yeah. Thank you. Then we have a question from Mr. Amritlal. K equals ULE. The earth fault factor is calculated using complex impedance Z1, Z2, and Z0 for positive, negative, and zero sequence system, symmetric compounds, taking into account the fault resistance R. The system is considered effectively earthed if the fault. I think it's not a question. Amrita is making a statement. It looks like a statement.
No. Actually, this definition does not appear. This the only definition that appears in anywhere about effective grounding is in the Green Book only. Maybe I would like to know the source of this definition. A system is considered effectively earthed if the earth fault factor K does. I would like to know the source, any standard. I remember this is earth fault factor. The surge arrestor application guide gives a graph showing the ratio of x0 by x1 and r0 by x1. So it is r0 by the ratio between r0 by x1 and x0 by x1 only. There is a graph in the application guide of like IEC standard for application guide of surge arresters. So I will recall it. I will produce the curve. I have made a presentation on selection of surge arresters. In that I have this. I do not know. I request Mr. Amritlal to share this source for this definition, 1.4, all those things. Then I will study and get back.
If you can unshare the screen, would be nice. If you can stop sharing the screen.
Okay.
Then the screen will be better. Then the speaker will come on the screen. That is why. So the next question is from Mr. Rahul P. Ajit. In a distribution transformer, the transformer is placed at 1 kilometer away from the house. If suppose there is a fault current generator, is it back to the distribution transformer through neutral earthing?
How it will? I don't know. Can you repeat?
The transformer is 1 kilometer away, and in case of earth fault in the consumer premise, will the current go back to the neutral through the earthing?
Of the transformer or of the generator?
Rahul, yes, of course, current has to return back.
Kirchhoff's law always says that the current will return to the source neutral. Wherever, irrespective of the length, if the transformer is feeding, the fault current will go back to the transformer neutral. If the generator is feeding, the fault current will go back to the generator neutral. Yes, if both the generators are neutrals are linked together and not isolated, unfortunately, but rules mandate isolation of the neutral. Suppose I'm assuming that both are interconnected, there will be a potential rise on the other source neutral. Suppose you have a generator, you have a transformer, both are feeding. When transformer is feeding, generator is not feeding, and vice versa. You have breakers for generator, you have breakers for transformer. Let us say you have only 3-pole breakers. You have interconnected the neutral. Whenever transformer is feeding and there is a fault in the transformer system, when the transformer is feeding, there is a ground fault in the system, the fault current will definitely return to transformer neutral only. But there is a danger, since the fault current is returning to the PE conductor or the earth conductor, there will be potential rise, voltage drop proportional to the product of fault current into resistance. There will be a potential voltage appearing at the generator neutral terminal also, because neutral is not isolated. The other thing is also true. If the generator is feeding and the neutrals are linked, the transformer which is switched off will have there will be a potential at the neutral of the transformer. That is why standards mandate at least one 4-pole breaker, either at the generator feeder breaker or at the transformer feeder breaker or at the bus coupler. At least there should be one place neutral. When the sources are separate, the neutrals must be isolated. This is IS 3043 very clearly documents with a lot of pictures also.
Yeah. Sir, then there is a question, how can we test the effectiveness of solidly earthed system, solidly earth grounded system? Okay, solidly earthed system.
Earth resistance only, you measure the neutral to earth resistance. Only no, in resistance, earth system, it will be very high. In effectively earth system, the resistance value should be as low as possible. That's all. How else you will? Yeah. Resistance only. Effectively, we call resistance. The resistance should be as low as possible. That is what the definition given in IS 3043. You measure the resistance, neutral ground resistance. If the resistance is very low, the system is effectively earthed. Definitely, the standard says that no, R0 by X1 has to be less than 1. You know your system positive sequence impedance. Since you are an engineer, electrical engineer, you should know what is your system positive sequence impedance, negative sequence impedance, and zero sequence impedance. If the sequence impedances, industrial networks, resistance is kept very low, the component, any impedance is R plus JX. So generally the R component is kept very low because that is dissipation of energy. X component is kept very high because it is utilization of energy. So generally R is negligible. So we say, instead of saying positive sequence impedance, negative sequence impedance, zero sequence impedance, we say positive sequence reactance, negative sequence reactance, and zero sequence reactance. Generally in any industry, the positive sequence reactance will be very high compared to the resistance part. So in solid earthing, the R0 or the zero sequence resistance, the resistance of the earth fault path compared to the ratio of R0 by X1 should always be less than 1. So you know your X1, you measure your R0 or earth fault loop impedance, what they call nowadays. You measure your R0, you compare your X1, R0 by X1 ratio. If it is R0 by X1 ratio is less than 1, your system is solidly grounded.
Okay, so there is a question. So in single phase to be earth fault, not only zero sequence current, but negative and positive sequence current also possible due to capacitive currents. Is it right?
Yes, all currents will be there, but it will be more. In zero sequence network, there is no sequence at all. When you are calling zero sequence, the very term zero sequence is there is no phase sequence at all. It does not follow any sequence. So in zero sequence, only all the vectors will add arithmetically. There is no negative sequence, there is no positive sequence. The very term says that zero sequence. Zero sequence means there is no phase sequence. There is no positive sequence, there is no negative sequence. So it is zero sequence itself is all the currents will add arithmetically, not vectorially.
Yeah, thank you, sir. So now there is another question. What you suggest earthing in coastal zones where the deterioration in continuous, I think he's talking about the earth electrode, what life of continuity, I think the deterioration or the degradation of
yes, sir, I would request the gentleman, sir, take your time, please read IS 3043. IS 3043 in one particular section very clearly gives corrosion allowances. And there is a table for different types of resistivity. What are the various corrosion possibilities? Corrosion ratios is clearly given. Even I think in IS 732 somewhere also I remember in some IS 3043 definitely mentions this corrosion allowance. So in coastal areas definitely you have to have allowance for corrosion. So please go through IS 3043 that clearly documented this answers this question.
Yes, thank you, sir. Actually, I have a different view there. These data which is there in IS 3043, these are very old data. It's time to upgrade these data.
Yeah, that is right. That is again always even GKG If you see the formula for earth fault current in IS 3043 is wrong. It mentions in the denominator it should be x1 plus x2 plus x3 plus 3 into x0 plus xgp. It is given x1 into x2 into x3.
Yeah.
I have written to BIS, they say they are reviewing and the next edition should be corrected. So many things still need to be corrected. Maybe we can contribute. We can give our inputs to BIS.
We have taken up the next revision of IS 3043, and I think seriously we have to look into this subject. The question is, where is the proof? For example, at the moment, the corrosion allowance given is, let's say, 20%. If more is required for an area where the soil resistivity is less than, let's say, 20 ohm meter, where is the study report? Sufficient reports are not there.
Yes,
So
sir.
this,
Yes, sir.
as you said, in America, there are several reports coming for resistance.
Geological reports, yes.
Such informations are not there in our country.
Yes, yes. Nobody has perhaps done a study. I remember in long back in way back in 1993-94, I was working in Visakhapatnam. We did earthing for an industry very close to the coast. See, those days, this much awareness was not there. They told you put a pipe earthing, we put a GI pipe earthing. After 1 year, we went and pulled the pipe. Only 1 feet pipe came out. So the bottom full portion was corroded because it was a saline soil. Full portion got corroded. After 1 year, they were frequently getting equipment damages because high voltages during earth faults. So they complained. We went and saw. We could literally pull out the earth electrode with our hand. 1 foot electrode, 3 meter we have put 1 foot electrode came out. The entire bottom portion was corroded.
Yes, actually these areas it need improvement. So whereas other side, I think BIS mostly are getting questions about this chemical earth. People are asking to make a chemical earth as a part of the standard, which anyway is.
Of course, long back when this chemical earthing was promoted, I used to get lot of pamphlets. I was at the L&T training center conducting various earthing classes. Then I used to question them. You are putting backfilling compound chemical. What chemical? After all, it is a different combination of bentonite, marconite, and you are adding some salts to it, magnesium sulfate, calcium, something like that. You are adding. That's all. Only what is the big secret about it? Nobody was able to answer. No manufacturer of chemical earthing. I wrote to almost all of them. Nobody could answer. Still, the question is unanswered. What is the chemical you are using? They have not answered it. They say it is a trade secret.
Okay, anyway, that's a different subject. Now, coming back to the question, somebody is asking, can you explain about UPS earthing?
It is a big subject to be discussed in a separate webinar, sir.
True, because the subject of electrical separation is not understood or it's rarely understood by the users.
Yes.
So UPS earthing, first question to be asked back is, are you electrically separating the circuit? Because nowadays most of the UPS doesn't have electrical separation.
No, for the time being, maybe we will cover this subject in a subsequent webinar. For the moment, I recommend the gentleman to go through Green Book. IEEE 142 Green Book. Green Book has got a very good chapter on UPS earthing. One entire chapter is dedicated for UPS earthing.
Yeah. There is also an IS standard on UPS. I forget the number.
Maybe I am not aware. Maybe.
So, sir, then from Mr. Abhishek Sarkara, it is shown, because you have shown one system rotating machines, you can go for a resistance earthed system, and for the other system, you can go for a solidly earthed system. So his question is, it is shown for LV rotating machine to have two connections, one with the resistance grounding for rotating machines and with the other without. Does it mean, let's say, for an apartment DG requirement to have two numbers, that is one for lighting load and the other for rotating load or high heating load?
Sir, simple, sir. If non-electrical professionals are handling electrical equipment, wherever there is a apprehension that non-electrical people, unauthorized people can handle electricity like lighting circuits, heater circuits and all, you must go for solid earthing only. If you are very sure that non-electrical person, unauthorized persons will not handle electricity, I am very sure I am having a permit to work system, I am having very good authorization control. In that case, you can definitely go for resistance earth system to protect your equipment. But you have to be very careful in a resistance earth system. You please don't allow unauthorized people to handle equipment in that zone. As simple as that.
In simple words, if we say, if normal people, common people are handling the system, it should be a solidly grounded.
Yes. By standard.
And if skilled or instructed people or people under the supervision of skilled or instructed people are handling, then resistance earth the system can be.
Yes.
That is a, yeah. So then there is a question: how can earth fault in MV system be cleared in 10 milliseconds when the circuit breaker, VCB or SF6 tripping time is 40 to 50 milliseconds?
Sir, clearing in the sense, whenever we say clearing in the sense, it is the relay time. 10 millisecond today, the arc protection devices are capable of sensing and sending a signal to the breaker in 10 millisecond. 10 millisecond is the, whenever we talk of any protective device, the time discussed is that of the protective device. I am not discussing the circuit breaker because the circuit breaker tripping times can vary depending upon the rated voltage, depending upon the fault current to be interrupted, depending upon the mechanism, depending upon the auxiliary voltage. There are n number of factors, variants are there, due to which the operating time of the switch gear can vary. So this 10 millisecond I am talking is that of the protective device. You add whatever your switch gear operating time to that. That will be the total fault clearing time.
Yeah, thank you, sir. There are two questions from two gentlemen asking the same question. NGT secondary resistance calculation, those slides, can you explain one more?
Okay. I will try to.
Your screen is already shared. You have to select the right slide.
Okay. So this is the one you are talking. I have not per se exactly added a neutral earthing. I just wanted people to understand the theory that when you connect a very low value resistance in the LV side, it will be reflected as a very high resistance on the HV side. This is the basic transformation theory. That is why any load you connect prior, even though the secondary current is more, the primary current is very, very less because the resistance connected low resistance added in the secondary appears as a very high resistance in the primary. So the HV side current is always lesser. Now, if you see this left hand, I am trying to explain once again. If you see the left hand portion of the slide, I have connected a 1000 ohm resistance on the HT side. I have connected a 5 ohm resistance on the LV side, maybe a load resistance, let us say. Now, to limit the HV side current to 12 ampere, my intention is to limit the HV side current to 12 ampere, for which I have connected a 1000 ohm resistance on the HV side. Now, the LV has got an integral resistance of 5 ohms, system resistance or whatever load resistance I have assumed. Now, if you see the 5 ohm resistance of the LV, multiplied by the transformation square of the transformation ratio. Transformation ratio is 11,000 by 240, whatever it is. You square it and multiply the 5 ohm. It will appear as a very high resistance, 10,503 ohms. The 5 ohm resistance you have connected in the 240 volt side, when you multiply by the ratio, turns ratio square, it will appear as a 10,503 ohms on the 11 kV side. Now, there is already a 1000 ohm resistance in parallel. the net resistance, parallel resistances R1, R2 by R1 plus R2, the effective resistance will be 913 ohms. When you connect 913 ohms in the HT side, the current will be 11,000 by 913, somewhere around 12 ampere. In the right hand slide, to achieve the same result, I am not connecting a 11 kV rated 1000 ohm resistor on the HT side. I am connecting a 240 volt rated 0.476 ohm resistor on the LV side. Now, if you do your calculation, effective resistance on the secondary side, that is parallel resistance R1, R2 by R1 plus R2 of 5 ohms and 0.476 ohms. It is 0.435 ohms, secondary effective resistance. If you multiply this 0.435 ohms by the turns ratio square, 11,000 volt by 240 volt square, you will get 913 ohms in the primary. When you get 913 ohms in the primary, the current is 12 ampere. You see, in both the cases, the primary current is 12 ampere. My intention is to limit the HT side current to 12 amperes. In left hand side, I am achieving that by providing a 1000 ohms 11 kV NGR or resistor. In the right hand side, I am achieving my goal by connecting a 240 volt 0.476 ohm resistor. So, which will be economical. So, we always say that advantage of NGT lies in going for a very low value resistor insulated to a very low voltage. The cost of the resistor and the size of the resistor box will be very, very negligible compared to connecting a high voltage resistor in the HT neutral directly. This is what I wanted to convey. You can do your own set of calculations. This will be, I think, in the recording, this slide also will appear, or you can even write to me. I will share this slide with you.
Yeah,
you can do
that's
your own calculation, because I don't want to go into the fundamental calculations of R1, R2, R1 plus R2. All these calculations I have done separately and put the values only here. You are at liberty to make your calculation and verify.
This is just to explain that this is how it works. Balance we can, each engineer can do.
Pardon?
Thanks for this. This is, you have made the calculation as an example. So the engineers involved can make their own calculations.
Yes, for any value, any arbitrary value, I have taken some arbitrary value. You are at liberty to put any other value on calculator.
Yes, correct. Thank you, sir. Now we have a question from Mr. In telecom installation data centers, which earthing is preferable? Where neutral carry harmonic current also? I don't know the meaning of this question. Of course, it is solidly earthed system.
If it is LV, data center is LV. LV is solidly earthed only. Please remove any myth you have that you can escape by providing any reactance earthing so that you can limit harmonic currents. No. If you are talking of LV supply in the data center, it must be solidly earthed only. Yes, if you are apprehensive of harmonic current, triplen harmonic currents, you provide 200% neutral. That is the latest practice. People are going for 5 core cables nowadays, 3 core for phase and 2 core for neutral. So initially it was 50% neutral, then it graduated to 100% neutral, and today people are talking of 200% neutral. If your data center, it is go for solid earthing, measure the triplen harmonics current. If the triplen harmonic current is very high, more than even the 100% neutral, go for 200% neutral. That is the general practice rather.
Thank you, sir. But in here, I have one question. You have to clarify to people, because a lot of time I used to get question that harmonics and earthing, how they are related. Can you put some light on it?
Sir, please understand the nature of any zero sequence current is to accumulate in the neutral. Zero sequence currents will accumulate in the neutral, because zero sequence currents are, as they say, they don't have any sequence, they arithmetically add and accumulate in the neutral. Triplen harmonic currents are zero sequence in nature. There is a sequence for every harmonics. They say 3n by 1 formula. 1 is positive, 2 is negative, 3 is 0, 4 is positive, 5 is negative, 6 is 0, and so on. You can build a table. Now, let us not worry about positive sequence and negative sequence harmonics, because they don't have anything to do with the neutral. All the triplen harmonics. Triplen harmonics in the sense odd multiples of 3. Odd multiples of 3 means 3, 9, 15, 21 and so on so forth. You take a third table, remove all the even numbers and whatever you get balance is called triplen harmonics. The nature of triplen harmonics is to accumulate in the neutral. This is the relation between harmonics and earthing because it involves neutral. Because neutral involves earth, solidly grounded system, it involves earth. Triplen harmonics have a relation between system earthing and neutral because it is flowing back to the neutral. We say it plays a role in system earthing. Triplen harmonics only. Triplen harmonics are generally anticipated in single phase electronic loads, single phase non-linear loads. Most of the data centers and computers and lighting, CFL lighting, LED lighting, fan regulators, all these in single phase UPS, all these things are generators of triplen harmonics. So the relationship is triplen harmonics with earth. This is the relation. There are good publications available in a website called Leonardo Energy. I will share in the group. Leonardo Energy has published very good publications on earthing, harmonics and power quality. There are some 20 different publications are there. People are free to download and they can study. People who are having interest. I will share the address. Leonardo Energy, LEONARDO, Leonardo Energy. They have got some very good publication. Capacitors, power quality, power factor improvement, earthing, harmonics, excellent publications are available. Those who are interested, please go through.
Yeah. So now there is the next question. How line to ground fault current is equal to LLN fault?
LLN fault, yes. Actually, the IS 13234 formula, if you see, the IS 13234 formula, it says CUN root 3 CUN by 2Z1 plus Z0. So positive sequence impedance, negative sequence impedance, and if your zero sequence impedance, the 13234 also says if your the zero sequence impedance can be lesser than or maybe equal to or maybe larger than your positive sequence reactance or positive sequence impedance. That is a statement in 13234. Now we have to always design our system for the worst condition. If your zero sequence impedance is more than your positive sequence impedance, no question, fault current will be lesser. But when I design my system, I have to design for the worst condition. So I assume that it is equal. When zero sequence impedance is equal or lesser, the fault current, when you put the zero sequence current is equal to positive sequence impedance, it becomes Z1 plus Z2 plus Z0 is equal to 3Z1. When you say the numerator is root 3 UN. Root 3 UN is again, you can say root 3 into U phase. That is 3 UN. Numerator is 3 UN. Denominator is 3 Z1. 3 UN by 3 Z1 is UN by Z1. UN by Z1 is the formula given in IS 13234 for 3-phase symmetrical short circuit current. So we say by derivation, if the zero sequence impedance is equal to positive sequence impedance, then the single phase to earth fault current is equal to 3-phase symmetrical short circuit current. People can make a reference to people can refer IS 13234. In that, this is clearly explained how to calculate the single phase to ground fault current.
Yes, thank you, sir. Now there is another question. How ground fault current affect the machine core in rotating machines? Also, I have a request to Dominic. Sir, can you make me as a co-host? Sir, Shivakumar, sir, please go ahead.
Yeah.
Yes, I will make it.
Now I will explain. This is, sir, how in any rotating electrical machine, the windings are in stator slots. The earth fault happens when the winding insulation damages and the current carrying winding conductor makes a connection with the core slot, that is core slot. Core slot is made up of iron material, which is high resistance material. Nevertheless, the core is connected to the yoke of the machine. The yoke of the machine has got a earth terminal. The earth terminal is connected with an earthing conductor. So the path for the most probable fault for any rotating machine is winding short circuit with the earth. The winding short circuit with the earth can always happen only through the core material, from core material to the yoke frame, from the yoke frame to the earth conductor and to the earth grid, and so back to the source. So invariably it will involve core of the machine. When this core carries this fault current, definitely because of the high resistance of the core material, definitely the heat produced will not be tolerated by the core lamination. Many times we have seen the core laminations, they are supposed to be lamination, they weld and stick together, they become a block. So this is what happens. We have seen, I will try to post some photos also. We have seen in 3.3 kV motors, the core is becoming a single block, molten and become a single block due to the earth fault inside the machine. This happens generally.
Thank you, sir. So now another question. We have actually a few more questions. Would be some of the questions are not serious, which I am trying to skip, and 2-3 questions I am trying to club together. So 2 questions. In solidly earthed system, it was said that neutral of the transformer shall be connected to MET and earth grid. When MET is already connected to earth pit and then to earth grid, then is it necessary to connect neutral directly to the earth grid? I didn't understood the question fully. So, gentlemen, if you are talking NEC Part 1, Section 18, first of all, and there is one more question. Can we connect MET to neutral earthing of transformer? So the answer is yes, MET has to be neutral, not neutral earthing. Neutral terminal of the source has to be connected to MET. That is the correct word.
Yes, so, IS 732 many times GK sir and myself have discussed this. There is a clear picture in IS 732 which says an MET, all your earthing is connected to MET, transformer, neutral, equipment, body, your lightning arrestor, LPS system, electronic system, everything is connected to an MET. MET is connected to your earth grid is connected to earth pits. Please understand, there is a class in IS 3043. I can't recollect the class number, but definitely it is shown. Take 2 connections from the transformer neutral, one to be connected to the earth electrode, the other to be connected to the earth grid. There is a clear mention of it in IS 3043. I believe I will try to recollect and post it in our WhatsApp group. So ultimately, yes, MET, earth grid, earth pit, all are interconnected. So you have to connect the MET, means you are connecting as well to the earth electrode.
Somebody asked a question, can you add me to your WhatsApp group? Actually, our WhatsApp group, this is a members group of NFE. Member, then automatically you are added to the group. So please become member in NFE so that not only this subject, we are daily tons of technical discussions are going on in the NFE group. So not only that, you can also participate in several of our programs. So now, sir, another question. This is about the solar PV. 1200 kWp solar rooftop plant generation inverter AC voltage injected to secondary of transformer 11 kV 500 volt transformer neutral kept floating. Please help to understand the reason.
You please share the SLD. Sitting here and
yes, this is not actually related to today's topic. This is totally a different topic. So here, gentlemen, you have to refer to the inverter manufacturers'
recommendation. And I think NEC does have a topic on solar earthing also, I believe.
Exactly. In part 8, this is explained. You have to look at
it. Is the solar earthing.
There are different techniques explained so that the fault at the DC side can be, the people can be, shock protection is achieved. You have to look into that. So,
see, generally, I have observed, because I have been part of supplying high voltage switchboards to various solar projects, maybe more than 300, 400 installations I have seen. The general practice in solar installation is the inverter transformer, LV side neutral, they don't connect to earth to avoid circulating currents, because these inverters generate a lot of harmonics, and to avoid this circulation currents, the triplet harmonic circulation currents, they say, I am surprised why you are not grounding the neutral. They say we want to avoid circulation current. Generally, in almost all the solar projects I have seen, the inverter transformers LV neutral. It is again a DY transformer. LV side is star and ST side is the 33 kV side is the delta. The LV neutral 380 volt or 690 volt, whatever neutral, LV side neutral, they keep floating to avoid circulating current.
Sir, there is a different reason as well, because the inverter, the inverter, that means inside the inverter, a functional earthing is already provided. And the functional earthing is made through a relay or through a fuse, HRC fuse. So 25 kilowatt solar PV, the HRC fuse in the functional circuit is 1 ampere. That means in case of any DC fault, and if the fault current is more than 1 ampere, the functional earthing is disconnected. The inverter will find out, the inverter will detect that there is a fault. It gives the alarm, but there is no hazard, because then the system becomes a floating system, and the fault comes into the picture. So that is actually, it's an accepted system. It is explained in part 6, part 8 of NEC. So now there is Mr. Rajiv, what is the recommended resistance value to avoid core damage in rotating machines?
I have mentioned the presentation. Please contact your rotating equipment manufacturer and collect your core damage curve. I have collected in my experience, whenever critical motors are there, high capacity motors and high voltage motors, I have invariably collected core damage curve. The core damage curve, I and T values. There is a I value, there is a T value. I have shown the graph also. The graph will be something like that. So you go by the core equipment manufacturer's core damage values. You collect from him. Generally, in almost all the machines I have seen, it is generally 25 ampere for 1 second. So even we don't allow to go to 25 ampere, we generally keep 10 ampere. High resistance grounding, we always keep 10 ampere only as the NGR current, limited fault current.
Yeah, sir. Now, actually, few people are asking to share the typical earthing layout of LV system and all. To all these answers, the simple answer to you is, please open the National Electrical Code Part 1 Section 18. There are pictures available. IS 3043. There are pictures available. You should do.
Yes.
There is nothing like a typical earthing layout which can be implemented everywhere. It depends on your plant layout. That is also written in IS 3043. The earthing grid or the design should be as per your plant layout, electrical system layout. So we cannot make a typical line and give it. Also, you should understand the reason and the meanings and then implement it properly. So one question, earth grid, neutral earthing and lightning arrestor earthing typical layout. Please refer the standard. These pictures are already there. Thank you for those questions. Now, how much potential difference is acceptable between neutral and earthing in solidly earthed system? This is
$1 million question. Yeah, there is a reference in the standard. I will produce. Recently, I had a discussion. I forgot. I will just recollect. Yes, there is a standard guidelines. Is there somewhere around 2 volt or 3 volt is there? There is a mention in the standard. I will reproduce. In our group, I will post it. But you need not per se worry much about the neutral earth potential.
No, actually, there is a very simple to understand. Say example, the voltage drop allowed in a typical installation is, let us say, 10 volt. That is the voltage drop allowed 10 volt. Now you have a solidly earthed system. The neutral voltage drop may be 50% of 10 volt. Let's say 5 volt. If the neutral voltage drop is more than 5 volt, the overall voltage drop at the end circuit will be higher. So you have to calculate in this way. This is a simple technique to understand it. So now sensitive earth fault should trip HT breaker in case of generator as it shut down. Message to prime mover. Your views?
Yes, sir. See, in generator, when we talk generator, we understand we are talking of power plant generators. Yes, there are in power plant generators, there are some class A, class B, class C, class D. There are types of faults. For certain faults, only the breaker is tripped, only the alternator is isolated. For certain faults, the prime mover shutdown signal is given. It is mentioned in application guide for generator protection. IEEE guide is there. So we have to react as per the guidelines given class A, class B, class C, like that. So I am not able to recollect now, but there are classes available. I will try to send you that document.
Yes, thank you, sir. Thank you. Somebody is asking zigzag transformer grounding. Yes, of course, this subject will be taken up in the next webinar, as Shivakumar sir already told. We will discuss this subject in the next one.
Yeah,
So-
there is a separate session we'll have on zigzag transformer.
Yes. Now there is a question: what is the difference between earth conductor and PE conductor? So the answer
Spelling.
is from the
Spelling.
no, sir. The definition which is given.
Really?
The earth conductor means any connection from the MET to a buried earth electrode is earth conductor, and anything which is running along with the phase and neutral conductor is a protective earth conductor, because protective earth conductor is supposed to carry substantial amount of fault current. So the sizing is very important. You have to size it according to the expected fault current, whereas earthing conductor, you don't need to size like a PE conductor. Some fixed sizes can be. Here, earthing conductor, important subject to be considered is the corrosion and the mechanical strength. The PE conductor, fault current. So
Yes.
these are the things. Now, actually, this subject, a lot of places people try to. It's a confusing subject. Sometimes it's told as PE conductor, sometimes earthing conductor, sometimes equipotential bonding conductor, and it is a little bit confusing. Now, sir,
And
the
again,
next.
there are precise definitions given in 3043, protective conductor,
Yeah.
Sizing of protective conductor, earthing conductor. I think there are some definitions available in 3043.
Exactly. In 3043 as well as in IS 732. 3043,
Yes.
the values are a little bit old, but IS 732 is internationally accepted values from IEC 60364. So, is it necessary to connect resistance earthing to 11 kV 415 volt 5000 kVA transformer, or a solid earthing is sufficient? Please clarify.
Sir,
Right?
what is the vector group of the transformer? If you are talking 415 volt side, definitely solid earthing, only solid earthing, only solid earthing, only solid earthing. Don't go away from that. By regulations, you are supposed to connect only by solid earthing, 415 volt side. 11 kV 5 MVA transformer, 11 kV by 5 MVA transformer is generally a delta star transformer, DY11. The primary side 11 kV side is delta, there is no question of neutral, no question of neutral earthing. The 415 volt side will be definitely star connected. There will be a neutral. DY11 means neutral will be produced out. So you must only solidly connect as per the regulations. Or if you are very sure that common public will not handle, you can provide a impedance earthing or resistance earthing. But again, take care to take the drawing approval from CAG beforehand.
Yeah, then there is a question. In case of VFD driven motor, how to earth the shaft voltage generator, and what should be the safe limit of voltage of shaft voltage?
I have to refer to the document and answer. I don't have a ready-made answer. I will reply.
Actually, here the VFD manufacturer, for example, ABB, they have very good documents which very clearly explains how to handle this particular situation, shaft current or the leakage currents through the bearings, how to handle it, how to make the bondings. All these are very well explained in the manufacturer's catalog.
Yeah.
Refer to that. Also in the drive standards, also it's explained. So you can refer to the manual. But again, I have one more recommendation. Please refer to the international manual of these manufacturers, because when it comes to India, the manufacturers are changing lot of technical information. The correct information is not circulated. So go to their international website, download the manual of, for example, ABB ACS 500. You go to the Swiss or some UK website and download the manual. You will see with pictures and the explanations. Thank you. So by this, I think almost all the questions are over. Let us close the question answer. And now, probably if any of the attendees wanted to ask some questions, Mr. Rajiv Agarwal, you can unmute yourself and ask the question. Also, Mr. Ajay, probably these two are the only questions at the moment. We've closed with this. Mr. Rajiv?
Yeah. Good afternoon. Thank you for a very good presentation. Actually, my question got answered because, like I was asking for rotating machines, what should be the, I mean, if it is a unit transformer feeding a 13.2 kV motor, what should be the recommended resistance value? So depending on the damage curve, I explained that 10 ampere.
Thank you, Mr. Rajiv. Thank you. So your question is already answered. So the question to Mr. Ajay, Mr. Ajay Pagaria, you have any questions or there is no question? So, Dominic sir, over to you. Almost the whole session is over. Now we are also overshooting the time, almost reaching 2 hours.
It's very eye-opening and very good subject. I could see a lot of good testimonial coming for Mr. Shivkumar for taking up this topic. And if you read the chat box, they're saying they were never knew this subject so well. So what we are doing is now this will be on our blog on NFE. When you go to blog, you'll get the recording, and also you can share it to all your colleagues and friends. And we will be coming back again soon on earthing related subject, probably in the last week of August, subject to Mr. Shivkumar's availability. And as I said, next 19th, we pasted the link to register. We are talking about we have two subjects, overcurrent protective, focusing on overcurrent protective devices. This will be presented by Krish. And again, we are talking on 26th. So it's a very interesting session. Again, we'll be sending separate link and to all my friends. Please join NFE. If you've seen the subject, if you could join and see the group, the technical matters that we are discussing is for most of them, it's a eye opener. So if you want to be a real professional electrical engineer, so do join our association called National Federation of Engineers for Electrical Safety. The website is given. I want to thank Mr. Shivkumar for sparing valuable time. God bless you, sir, for sharing your knowledge of your 40 years of learning that you have done. I always believe first 25 years of our life is all about learning. Next 25 years is all about earning. The next 25 years is all giving. So after once you turn 50, it's all about giving. That's what Mr. Gopakumar is still not 50, but Shivkumar and me have turned 50. We are giving away to the society. This is the website of NFE. It's simple. Less than 2 minutes, you become a member. And you'll get your PDF member certificate, you'll get payment receipt, you'll get welcome address by the president. And it's just one dinner with your family. That is the cost of the membership. One dinner with your family, you will be becoming a professional member of NFE. I urge once again, all the students who are listening for this webinar, please do. We also have a student membership. It's just a 500 rupees, less than a cost of a pizza. Okay, so let's see how many members, how many students going to become a member. And we have a blog here. You can see the blog. All our webinars are linked here, and many blogs are there, many articles are there. So you could probably join, and yes, you can see the many. You can see that how many subject we have covered in last 4 months. It's a rich of knowledge, it's full of knowledge-based, website that we have. And we are here, a lot of professionals with 50, 60, 70 years of experience can shed a lot more lights on it. So thank you so much, my dear friends, and I look forward to see you on 19th again for our webinar on protective devices. Thank you, our moderator, Mr. Gopakumar, and also the president of NFE. A lot of energy. He was in Pune, giving lecture in Pune, and now he's in Trivandrum, tip of India, and I don't know where he'll be by the evening. So let God give him a lot of strength and good health, and a lot of energy to him. And we are so happy to have Mr. Gopakumar, and he's making all of us to run around the country, preach. He's the evangelist of safety, electrical safety. God bless you, sir. God bless Mr. Shivkumar. A wonderful day. Stay safe, stay healthy. Thank you very much. Bye-bye.
Thank you. Bye.